Okay, hi everyone. So this is the next part for the video series of elementary number theory topics. So in this video, I'm going to explain the concept of fundamental theorem of arithmetic. Sorry, the proof of the fundamental theorem of arithmetics. All right. All right. So what fundamental theorem of arithmetic says? Fundamental theorem of arithmetics. All right, what it says. I believe it is pretty much understandable what I'm writing. It says that numbers, integers greater than n greater than 1 is either prime or product of prime, can be represented using product of primes. That's it. It says this product of primes. So the fundamental theorem of arithmetic says that the numbers greater than 1 can be represented is either prime or the product of primes. So we are proving this theorem by using the induction method. Now if we assume that n equal to 2, then the case will be trivial for this. So we are assuming then that the theorem is true for all integers greater than 1 and less than n. Alright. So for this, if n is prime, so the n will be greater than 1 and till up to n minus 1 we are using this, and if n is prime, then there is nothing to prove, right? Because what it says, it satisfies that either prime. If n is not prime, the n can be written in product from primes, p1, p2, pr. Alright. So for the sake of argument, I'm just having the n, the product of the n can be represented using other numbers, other factors. That is, we are assuming that q1, q2, qk exist. Alright. These two series divide this n. So from the analogy we know that these two must divide each other. So means there could be some number in this series which divide this number, and that number also, and there could be another number in this series that could divide this n. So that's why we got this. Alright. Now we just have to show that the numbers right over here is we have to show that r equal to k, and there is some pi in here will equal to some qi or qj, whatever you want to say. There is some pi in this series and there is some qj in this series, which are equal, because we know that these are all the list of prime numbers, and this is also prime numbers. These are also prime numbers. So if the prime numbers from this series dividing this prime numbers, so we know that it will only be possible when these two prime numbers are equal. Alright. So I'm just assuming that. Now the order of the numbers would be different from these two series, so it is not necessary for that. If you want to renumber this, you can renumber it, but here what I'm trying to do is that I'm taking some pi from this and dividing this series, this n by some pi, means I'm taking 1, because we have ordered the numbers, the list of numbers, so it is not it does not matter if I take p1, then what we have left with p3, so on, pr, q2, q3, so on, qk. So this p1 divides this p1. We have just excluded the prime from this series, which divides these both numbers, and we got this. That is 1 is less than n by p, 1 is less than n. from this we can conclude that as we have already removed this p1 from these both, so from this we can conclude that these two prime factors, the factorization of these n is equal. If not, we can do the process for n number of primes, and at that moment we can get it done correctly. So by this we can conclude that n is a number which is represented using product of primes. That's it. And also you can represent this product of primes as like this as well, n equal to, this is the product sign, I equal to 1 to k for pi. ai represent the numbers, powers of a number. Alright, so this is pretty much about fundamental theorem of arithmetic. That is pretty much easy, and I believe I'm able to explain you well. And next what we have here is okay, there is a theorem related to n equal to product of primes power some numbers. For this case I'm just explaining the brief of it. That is, there is a number n, we have already got it. So there is another number d that divides this n. So that means d can be represented using this formula, that is we have got it. So that is d can be represented if assuming that d equal to 1, because 1 divides every number, right? 1 divides every number, so d equal to 1, so that d can be represented using the product of primes p1 0, p2 0, pk 0 up to 0, sorry. So we know that power 0 will give you 1, so that means d equal to 1, and it satisfies the case in this case. So if I assume that d is not equal to 1 and 1 is less than d and d is less than n, and then at that moment if d divides n, so that means you can write this d in the product of different primes with their different powers of each of the primes. That is, you can represent d using the same product formula e2 so on pk power ak. Means these prime, there are different distinct primes and they all have distinct powers. Alright, you can also have the example. For example, if I take 2 100, this can be represented this, you can take out the LCM for this, you will get 2 square 3 5 square 7. Alright, so we got p1 equal to 2, p2 equal to 3, p3 equal to 5, p4 equal to 7, with a1 equal to 2 and a3 equal to 2 and p2 equal to 1. Alright, so you can compare it with the product formula. This is the basic, and by this I covers some basic concept of divisors and GCDs and the fundamental theorem of arithmetic. Now I am going to start the next concept, that is Euclidean algorithms. From this, before we going to start, that there is one problem that is given in the textbook that I just want to highlight, is that it says that this series 1 by Pn diverges, sorry, diverges, diverges. So we just have to prove this. This is a summation, this is a sum of 1 by Pn where n goes from 1 to infinity, and this is the infinite series. Alright, infinite series, we just have to prove that. it diverges. Now we are proving it by contradiction. We are assuming that the series that above is mentioned is a convergent series. So that means there exists an integer k such that we have built another series m equal to k plus 1 by pm is less than 1 by 2. Since it converges, I have selected it as it is less than 1 by 2. Alright, because we know that converging means it will be lesser than, it will go up to some x point where it will become 0. Alright, so I believe that I assume that this series 1 by pm is converging, so that's why I got a bond that is 1 by 2. Alright, now what we have here is that I'm going to take a number q. Alright, from this I'm going to take a number q that is equal to some primes p1, p2, so on pk, just using these prime factors of the q, and having 1 plus nq. For 1 plus nq is another number, and we know that no prime in this list because q is less than this 1 plus nq. So from this we know that these primes cannot divide this 1 plus nq. So from this there are other primes that could divide this, that is pk plus 1, pk plus 2, so on. Now by this we can have another series, alright, even more lesser, that is n equal to 1 to r 1 by 1 plus nq, using the same, is less than or equal to okay, why I have used this, I will explain you. Wait a minute. Okay, this is also series which is converging, this series also converging. Alright, I'm using this t equal to 1 to infinity, where t is over here, so I'm just adding all the sums of the series when we are scoring the when we are having the power of t over here. So to make this series is absolutely greater than the series that we have selected. So so to make this series even more converging, or even less even more smaller series compared to this, so from this we can write, alright, from this we can write summation n equal to 1 to r 1 by 1 plus nq is lesser t equal to 1 to infinity, the same t function we are using 1 by 2 or t, use it from here. So from this we got 1 by n plus 1 plus nq is less than or equal to summation of 1 by 2 of t. From we can write it right now. By here there it does not mention how we there is one test, we call it as comparison test. By comparison test we get that the series 1 by 1 plus nq, this series right over here, has bonds and it is converging. Alright, sorry for that. Okay, so the series right over here is 1 by 2 power t is actually a convergent geometric series. Alright, so that makes this series 1 by 1 plus nq has bounded partial sums. Hence we can, from this we can say that this series has it converges, which says which makes it which makes a contradiction, which arises the contradiction. So by using the comparison test or integral test, we get that this is a contradiction. We got it when we assume that the series 1 by Pn is 1 by Pn is converging sequence. So for that we got that 1 by, from that we can get that 1 by Pn is diverges, not converges. I can provide you the comparison test theorem as well. What compare, taking this 1 by 1 plus nq, alright, from 1 to infinity. This is a comparison test. Now naming the series an equal to 1 by 1 plus nq and bn equal to some other series that is 1 by n. Dividing this an by bn, we get n by 1 plus nq, alright, 1 by n plus 1 plus nq. Now applying limit n tends to infinity to an bn, we get 1 by hence from this we get that 1 by q is not equal to 0 by comparison test. From this, that implies that we got the contradiction that 1 by Pn is converging, 1 by n 1 plus nq is diverging. So hence we can say that 1 by Pn is diverges, 1 by 1 plus nq converges. Alright, so this is the theorem that is about summation of 1 by Pn is diverges, infinite series of summation. Now the next theorem that we have here is Euclidean algorithm. This is pretty much simple compared to what we have already done previously for the GCD of two numbers. Now we have another this theorem is pretty much similar to that one. Now we call this theorem as division algorithm. Okay, we call this theorem as division algorithm, the division algorithm. Alright, so we know that division algorithm of two numbers. We have already learned this in lower classes. The same thing that we have to do for this, is A equal to BQ plus R. This is the lemma, Euclid lemma, and we know that there are two numbers a and b, and from this we have constructed a set A equal to some set that is a minus bx such that x belongs to integers. Alright, a minus bx is greater than or equal to 0. There is a set. Now this set is clearly non-empty, alright, and it has a non-negative integer, non-negative least number, say r. Alright, and this S has a least number, say r. From this we can write r equal to a minus bq for some q, belongs to integers. Alright, so the least number that is a minus bx, what we have considered in the set S is to be equal to r. So we are presuming that S r is the least number. Now from this we can write we can write a equal to bq plus r, and r is less than b, right? R should be less than b. We know that if r is greater than or equal to b, we get r minus b greater than 0. If r is obviously if r is greater than b, we get r minus b greater than 0. That is, if 3 is greater than 1, alright, obviously 3 is greater than 1 or 3 is greater than 2, we get that 3 minus 2 or 3 minus 1 will be greater than 0. We know that, right? So from this we got this. The substituting the value of r in this case, that is a minus bq minus b is greater than 0. We get a minus, separating, taking out b common, q plus 1 greater than 0. We know that q belongs to integers. Q plus 1 also belongs to integers from that implies, and then it also implies that a minus q plus 1 into b belongs to s. That implies r minus b belongs to s. Because this is integer, just I have removed it, so we get that another least number, that is r minus b belongs to s, which is even lesser than the r that we have assumed earlier. So we got the contradiction. So hence we have where we get the contradiction, why we got this contradiction is because we assume that r is greater than or equal to b. Alright, so hence this is a contradiction. From this we can say that hence we got the contradiction. From this we can say that we can say that r is less than b, r is less than b, and the condition will be like this: a is equal to bq plus r, and that is 0 is less than or equal to r is less than b. So this is the Euclidean algorithm. And one more thing that we can add up over here is that we can also prove that this r right over here is unique. Alright, now taking the same numbers, a equal to bq plus r, another a equal to bq plus r dash. Alright, so taking a and b fixed, and whenever we divide this a by b, we get different remainders. So from this we have to conclude that bq plus r equal to bq plus r dash. Alright, you can cancel this out. You want to end up nothing with nothing. So bq minus sorry for that, one more thing, q dash, bq dash, and that's why we won't be able to cancel this out. From this we can take b common, q minus q dash, that implies b divides this r, that implies b divides r dash minus r, right? This is impossible, to be honest, because as b is greater than both r's, as b is greater than both r dash, r and r dash, let's take a number line from here 0, we have r, here we have r dash, and we have b. So b cannot divide the numbers which are less than the number, so r dash minus r is even more lesser than r dash. So from this we can assume we can say that from here we can say that r dash minus r mod, because we want these values to be positive, r dash equal to r. From this that implies if I substitute over here, that implies that you will get q equal to q dash. So by this we can conclude that r and r is unique. Actually, basically this r that we have previously believed that was a least positive integer in the set S. So r is a unique number. All right. And there are other theorems as well, that is if you take a equal to 3q plus r, then r will be less than the b, that then we get that equal to 3q 3a equal to 3q plus 1 or equal to 3q plus 2 at most. So the values of r will be from 0 to 2. If I take b equal to 3, I will get 3q plus 1, 3q plus 2. That's it, because we have strictly selected that r is less than b. We are not using equal to sign. Alright, now there is one more theorem, that is what we call it as Euclidean algorithm. Now I'm trying to go a bit fast from here onwards. I'm not going to give you step-by-step guide for each and every theorem. So here we are going to discuss Euclidean algorithm. Alright, so Euclidean algorithm, we just have to get the algorithm, that is r naught equal to r1 q1 plus r2. We are just replacing a with r naught and b with r1 to get the series of remainders over here, so that at some point we get a remainder which divides this r naught completely, and at that moment we consider that r is a GCD of this this lemma. Alright, now using the same concept of lemma, that is we get r2 q2 plus r3, r1 is getting multiplied by r2, this is the remainder into some q2 plus r3. Alright, the condition will always hold here, that is 0 is less than r3 is less than r2. Alright, the condition we have previously proved. We get this rn minus 2 at some point, alright, which is equal to rn minus 1 into qn minus 1 plus rn, and this rn minus 1 at the end, where we get rn qn plus rn plus 1, where rn plus 1 equal to 0. Actually this is rn plus 1 like this. So from this we get this is equal to 0. From this we can say that this rn is the GCD. We have to claim that this is the GCD of this. Now we can prove the theorem, right? The same thing, that we have to consider this a equal to some r naught and b equal to r1. This will be given in your theorem question itself, or if it is not given, then you can write it by yourself. It is easy. You just replacing r naught with a with r naught and b with r1. From that it follows. It is not a big deal. Now we have to prove that. What is we have to prove? That at some point, at some nth digit, nth stage, we get this r naught is getting divided completely. We conclude that the GCD of this it will be equal to this rn right over here. This actually not this. These both are pretty much same. These both are same, actually, not pretty much same. These both are same, but we usually denote GCD right over here, the number which is above the 0. Actually this is the GCD of number. We have to show it right over here, because where we got 0, we have to prove, we have to say that GCD is there. Alright, now what we have to do is that we have to claim that GCD of a comma b equal to rn. Alright, this is the equation. Considering this equation, we have to write n number of steps which can be derived from this. Rn divide rn minus 1. Here from here we got rn divides rn minus 1 by the previous number. That implies Rn divide. We have the value for Rn minus 1 that we can get from here. Alright, there is Qn minus 1 into Rn minus 1. Alright, since wait a minute. Alright, sorry for that. We get Rn divides Rn minus 1, that implies Rn divides Qn minus 1 into Qn Rn minus 1. Since we have Rn over here, then if this Rn is dividing Rn minus 1, from this we can write Rn can also divide this Rn minus 1 into Qn minus 1. Alright, from this we can write and also Rn divides Rn. Alright, that implies Rn divides Qn minus 1 into Rn minus 1 plus Rn. Alright, from this we can write from this we can write alright, Rn divides Rn minus 2. Alright, that implies Rn divides Rn minus 2, because if you observe that the value we get Qn minus 1 into Rn minus 1 plus Rn is the value of Rn minus 2. Alright, so from this we got Rn divides Rn minus 2. Now again you can repeat the process for you can repeat the process, that is there we are taking Rn minus 2 divides Rn divides Rn minus 2. Alright, Rn divides Rn minus 2, that implies Rn divides Qn minus 2 into Rn minus 2, and also Rn divides Rn minus 1. From the algorithm we get this, from there we get Rn divides Rn minus 3. Continuing this process, at some point we will get Rn divides R1, that is Rn divides B, and Rn divides R0, that implies Rn divides A. Alright, so we can write Rn divides A and Rn divides B. That is the GCD of the series. So from this we can conclude that Rn is dividing this A and B completely. Rn is dividing this A and B. So from this we can claim that Rn is a GCD of A and B. Also we can claim for the common divisors of this R0 and R1, because we have used this to divide, right? So you can also prove for Rn, R0 and NC even where we get this Rn divides this GCD of A comma B. If we consider a C, a common divisors of A and B, then a common divisor of A and B, from this we can imply that implies that this R, okay, I will write, we are assuming that there is a common divisor C which divides both A and B. Alright, not the GCD, just C divides A and C divides B. So if you follow the Euclid algorithm that I have already shown to you, from this you can get the same thing. If you assume that A equal to R0 and B equal to B equal to R1, from this you can get the same the theorem that I have already shown to you. You can follow those steps and you will end up eventually having C divides Rn. Alright, from this you can conclude that Rn is a GCD of a comma b, because obviously we have already proved that Rn divides a comma b in the previous case, and there is another number c which is dividing this Rn, so we can claim that the greatest common divisor of a and b and c is Rn. Alright, now there is one example where we can use this division algorithm. I'm just going to share you with an example. Right. Alright, taking some number, there is d equal to 119 and 272. The GCD of this 119 and 272 is d. A equal to 119 and d equal to 272. We are using Euclid lemma to prove the linear combination of A and B. Sorry, this is B. It's not actually, this is B. This is A. To make it more clearly, A is equal to BQ plus A should be greater than B, right? So now what we have to do is that we have to represent the 119 and 272 GCD as a linear combination of two numbers. That is, let's assume that the GCD of A and B is D. So you can have this D equal to some AX minus some BY or plus BY. Don't know. So this is a linear combination that we got it from here. So we don't know the values of x and y, so we have to got the x and y values. So this is pretty much easy. You just have to divide this 272 by 119, or you can find the GCD. 272 equal to 119 into 2 plus 34. Alright, taking the 119 and multiplying with 34 into 3, I will get 17. You can verify the result. I'm just writing directly from the book, okay, from the notes. And now we got the GCD, that is 17. Alright, 17 is the GCD. In the previous case, basically it is 17 is Rn. If you consider this 272 as R0 and 119 as R1. Alright, now this is now what you have to do is that we got the GCD, that is, you can write 17 equal to 119 and 272. Alright, so this is how you can write 17 equal, but we have to prove that we have to make it equal to a linear combination of two numbers, that is x and y. So actually right over here we get 17 equal to 119 and 272. That is the GCD of 119 and 272 is 17. This is 17. So what we have to do is that 17 equal to 119. I'm getting this from here using this. 17 equal to, we know that 17 equal to 119 minus 34 into 7 minus 34 into 3, sorry, not 7, 34 into 3. Now we have to keep these numbers safe. There is 119 whenever we get 119 and 270 2, because we want this A and B to be fixed. Just getting the values from these as per our requirement. Now we have to use the value for 34. we have the value for 34 is equal to right from here, that is 272 minus 119 into 2, so 17 equal to 119. all right, minus 34, the value for 34 is 272 minus 119 into 2, and also this 3. Now you can have directly, you can do it, that is we have 119 119 getting multiplied by 3 to 6, we have 119 minus or plus, we get 119 equal multiplied by 7. all right, we have minus into minus, we get sorry, not, we are dealing with this one, right? 3 into 2 7 2, that's it. No, we don't have any numbers. 272 into 3, from this we get 17 equal to 119 into x minus 272 into y, the same form that we got here. X is equal to 7 and y equal to 3. This is simple. Alright, so this is the pretty much end of that chapter. Now moving on to another chapter, that is arithmetic functions, that is mobius function and euler function. Alright, so I'm going to continue that in the next video. Thanks for watching the video. If you understand the concept and if you learned something from my video, then I would appreciate that you like my video, and if you would like my video and subscribe to my channel, and and stay tuned to watch more videos, okay, we will meet in the next video. That is, I'm going to explain the arithmetic functions. Alright, okay, bye.